Okay, it's a real pleasure to have Aloni Cohen from the University of Chicago here. Aloni has done a lot of great work. He started out as a computer scientist at MIT, but he's now branched out into law and all manner of other connections. So I'm sure he'll give us a great talk.
Thank you for inviting me. I'll clarify, I'm still a computer scientist. But yeah, I'm glad to be here and glad to be talking about this project, which I hope people here will find interesting. I'm going to tell you about a paper. The paper is available online right now on my website, but we're uploading to archive ePrint today. We just have to get past the archive uploading hurdles. But we are in the process of uploading it. And this is based on joint work with Adam Smith and Marika Swanberg and Prashant Vasudevan. Marika is a student at BU. So I don't know, if she shows up looking for an internship or a job in the future, you should totally hire her. Yeah, so let's get started. And I'm going to try to, people are going to leave at 1, is that right? Or at the hour, the next hour. So I'm going to try to keep time at the end for a discussion. Feel free to interrupt and ask questions. I don't know if there's a raise hands feature in Google Meet. Just interrupt and ask if you have any questions as we go. And so as Thomas said, my clicker isn't working. As Thomas said, I am a computer scientist, and I have branched out into law and all manner of other things. In particular, I try to think about how privacy law interacts with cryptography and privacy from the computer science point of view. So I'm a theoretical cryptographer, if I must put myself in a bin, and I think about how these things interact. And so I've done some work on GDPR, redistricting, some work on the Fifth Amendment. And I am telling you this because I feel like I have a reputation, so I need to give you a disclaimer. And the disclaimer is that today I'm not making any sort of legal claims and not making any sort of legal arguments. I'm just law and policy are sort of an inspiration, but we're still operating sort of only in computer science. So with that disclaimer, I want to tell you about data deletion, and I'll start with the usual story about data deletion and machine learning, which you may have heard about under the umbrella term of machine unlearning. And so this story, I'm not going to tell it to you myself. I'll tell it to you as told by somebody else. So I took some screenshots from a talk. A really, really great talk, I must specify. But here's the deletion and machine learning story. So various privacy laws or regulations provide people with a right to delete their data. So for example, the GDPR has a right to be forgotten, stating that the data subject shall have the right to obtain from the controller. The controller is the entity that is controlling people's data. Obtain from the controller the erasure of personal data concerning him or her without undue delay, and the controller shall erase the data. Right. So this is a right that the GDPR provides to European citizens. California provides a similar right. Canada does, and sort of all the laws that follow the GDPR have something like this. The new AI Bill of Rights blueprint that was put out last week has something like this. And so this is something that more and more people are thinking about and want to be able to provide. But what does data deletion mean? Because it's easy to delete data from like a database, a SQL database. But if that data was used for anything interesting, the effect of the data might live on, right? So in particular, in the context of ML, the data might have been used to train a model, and deleting the data from the data set doesn't change the model. And the model itself might be very impacted by a particular data point or a particular set of data points. And in particular, that can be disclosive, right? We know, everybody here knows that models can reveal some of the training data. And so the actual goal, so the usual story goes, the actual goal is to remove or limit the information about a data point present in the system including the data set here, the outputs of computations on the data set, and in particular, any downstream derivatives like machine learned models. So that's the problem and the motivation. And then we jump in this usual story to say that the ideal solution from a privacy perspective, the ideal solution is that when a deletion request arrives, you recompute everything, all models trained on the data set, you recompute them with the deleted record removed. You recompute from scratch. The only problem with this is not privacy, it's compute. That doing this every time somebody wants to delete is just prohibitively expensive. And so the problem of machine learning is to design faster ways of approximating this idea. This is machine learning. This is the story that all of machine learning tells. And it's a great story. So I want to be very, very clear. I wouldn't use these slides if I didn't think that the slides I stole them, the talk I stole them from was a great talk. Machine learning as a line of work, it's meaningful and it's technically interesting, and I like it, and I have only positive things to say. I particularly recommend these two works. I think they're the papers that I read that I think changed how I think or taught me the most. So I'm not trying to like pick on or disparage the line of work. But what I do want to try to convince you of is that this is not the whole story, and there's sort of more to the story. Yeah, there it is. So let's question the unlearning story. And so this text I took from those slides. The problem is that deleting from the database doesn't remove the influence on downstream models, which can be disclosive. The goal is to limit the information about a data point present in the downstream models. And the ideal solution is to retrain from scratch, right? That's the story. But I think there's a mismatch between the motivation and the solution. And as an example, this problem, the motivation, seems like DP could solve that problem, differential privacy. I'm assuming everybody here knows what differential privacy is. Seems like DP could solve that problem, right? If it's about the influence of a particular data point on the downstream model, and we want to limit the information in the model of the data point, I think I said that right, then if we did differentially private learning, seems like we would solve the problem. You can think about this in different architectures, like central DP with just a batch learning, you train on the data set once. Or if you're in an online setting, maybe pen privacy. But the ideal solution, DP is inconsistent with the ideal solution. Doesn't suffice. And so why is this? Let's just unpack the ideal solution a little bit. So here's the retrain. And we're going to talk about retraining, which is the ideal solution from machine learning, and this like DP approach, which I'm going to call for right now DP, and then ignore all deletion requests. So here's retraining. From scratch, you have a data set you train. I think this guy's name is Joe. Joe comes along and asks to be unlearned, asks to be deleted. So you do something to the trained model, and now you have a new trained model. And you compare the left side to the right side, which is the ideal retraining, where you retrained without Joe's data. So that's deleting Joe. That's unlearning Joe. And machine learning requires that these are close in distribution. The output of retraining and the output of train, then unlearn, should be close in distribution. Machine learning also typically requires that this is true if you delete multiple people. And in particular, if you delete everybody in the data set, one by one by one, then on the right-hand side, when you retrain from scratch on an empty data set, you get something completely trivial. So on the left-hand side, when you train and then unlearn everybody, you also have to get something completely untrivial. Sorry, completely trivial. You have to have trivial and trivial. Machine learning requires that what you get on the left is trivial. I think I messed it up, but that's what it's trying to say. So that's retraining. That's the ideal solution that machine learning gives. But differential privacy, and then ignoring deletion requests, right? If we take this intuition that DP provides, answers those motivating issues, then you can ignore deletion requests, do DP learning once, and you get something non-trivial, right? And so there's this mismatch here. And so the first sort of motivating question that I want to use to frame the talk is there some conception of data deletion that DP achieves? And is that conception meaningful? And right, like it's not a satisfying answer here to say differential privacy is meaningful, and therefore anything that's differential privacy deletes, because that's not really a way we understand deletion. That's just sort of that's like an axiom, a claim, a proposition that differential privacy provides some notion of deletion. But what is that notion of deletion, right? That's sort of question one. Any questions before I go on? No. Okay, but this is still not the whole story. I want to go beyond statistical computations. So here, sort of on the right, is sort of the picture we've been thinking about. You have some entity there's a data stream, at every time step, or maybe at the end of a bunch of time steps, they output a model. You can generalize this picture beyond learning, beyond models, to general statistical computations. But there are things in the world that aren't machine learning. I know it's hard to believe. So, for example, Twitter, right? In Twitter, some user Alice makes a tweet, and some other users also make tweets, and these other users might interact with Alice out in the real world because they're friends. They can respond to each other's tweets and retweet each other's tweets. And Twitter is like storing all these tweets in some complicated data structures and serving them out. This picture has nothing to do with the picture that was on the right-hand side before. In particular, differential privacy is it doesn't make any sort of sense for this functionality, right? So social functionality, we really want to interact with the people. We don't want to interact with like randomized response tweets. We want to interact with tweets. But we can still imagine that we want to limit the downstream interaction, the downstream effect that Alice's tweets have after Alice's tweets are deleted. Okay. And so there's a challenge of sort of how to formalize this. And what do we even want to require? So there's work before ours. This is a work of Garg, Goldwasser, Vasudevan. Sort of thinking about this problem, not in particular the Twitter context, but in this arbitrary interactive environment context. And they propose a definition that we call deletion as confidentiality. That's not the name they gave it, but it's the name we give it. And they imagine the real world on the left, which is sort of this arbitrary interaction that I described, as opposed to an ideal world on the right, where Alice doesn't tweet. In particular, just Alice doesn't interact with the controller, with Twitter. Here, Twitter is the data controller, Alice is Alice, and everybody else is the environment. So if I use those words before I've shown them on the slide, that's what I mean. So deletion as confidentiality requires that the real world on the left and the ideal world on the right are computationally indistinguishable. But the problem with this goal is that Alice's behaviors can affect the behaviors of other people in sort of arbitrarily complex ways, and you can't undo those changes. So, for example, Alice sends some tweet, and somebody in the world, Bob, responds to the tweet. Alice is super cool because she likes Star Wars, and she tweeted about it. That's in the real world. In the ideal world, if Bob is looking for Alice's tweets to decide whether she's so cool, then he, might tweet that he wishes Alice would tweet, right? The tweet on the right, the tweet that Bob tweeted on the right, and the tweet that Bob tweeted on the left are different tweets. Right? These worlds are completely distinguishable. And Twitter can't hope to like recompute the function that the environment is computing. So unrolling these dependencies is completely hopeless. So deletion is confidentiality. So what it requires is that other parties can't learn anything about what Alice does ever, at least not from the control. And so something like Twitter, social functionality is just completely impossible. So they show in that paper that other things are possible, but social functionalities are completely impossible. And so responding to basically this problem, there was another attempt at defining deletion by, I'm going to butcher their names because I think they're French, Cohen and Lemontaine. I don't know if I got it right. They propose a definition, sort of building on GGV. I'm going to call that definition simulatable deletion. Again, it's not the name they gave it, but I think it's clearer. So what do GL propose as a way to expand on deletion as confidentiality? They imagine the real world. And what they require is not an indistinguishability type guarantee, but a simulation guarantee. If you're a cryptographer, maybe that means something. And in particular, they require that the real world that results after Alice has deleted her data, so rather after the controller has deleted Alice's data, after Alice requested deletion, is simulatable given the view of the other parties, throughout the execution. In particular, everything the other parties know from before deletion can be used in this simulation of the world that is supposed to result after deletion. And if the world after deletion is simulatable in this way, it satisfies simulatable deletion. So a way to interpret this is that other parties, the environment, can't learn anything new about Alice after Alice has been deleted. Right? So this is seems reasonable. The problem with this is that in this particular example, Twitter doesn't have to delete any tweet that's ever been read. Right? Because if somebody in the environment read the tweet, then the simulator can simulate Alice's tweet. And so Twitter doesn't have to delete it from its internal state. So Twitter can just say, well, you want it to be deleted. You want to be deleted. Well, too bad. You shouldn't have tweeted in the first place. Right? That's an implication of this definition. And that also seems wrong. Right? That I hope that people here have the intuition that that's not the right outcome. So I want to suggest that both these definitions, deletion as control and simulatable deletion, they only care about confidentiality. And what I mean by that is that with deletion as control, if you don't, that's supposed to say deletion as confidentiality. GGV, the definition I had a second ago. With deletion as confidentiality, the GGV definition, if you can't guarantee confidentiality, then you just can't satisfy the definition. Right? And the simulatable deletion takes the other extreme, which is once you violated confidentiality, then you sort of satisfy the definition for free. Right? But they're both about confidentiality, and they sort of occupy opposite extremes here. I want to suggest that, and this work is sort of the whole goal of this work is to try to get at something different, in particular, something like control, what it means to control sort of these tweets. So Alice wants to delete her tweets, right? That's what she wants. She doesn't care that the environment knows the tweet necessarily. She knows that Bob has already retweeted her tweet and responded to it. And so maybe you could read Bob's tweets and figure out what Alice tweeted. She just wants to delete her tweets, right? And in particular, she wants to delete her tweets, even if doing so is more disclosive. So there's this work in the machine learning literature that shows that if you have sort of a model before and after it's been updated, it's been unlearned, that you can use the difference of those two models to learn something about the data point that was deleted, right? So unlearning can be disclosive. Alice doesn't give a damn. She wants to delete her tweet, right? Maybe it's disclosive. I don't care. I just want to be out of the story, right? And that's like a control thing, control notion instead of a confidentiality notion. I'm arguing. So in the case of Twitter, here's Alice. She tweets. Here's Bob. He replies to the tweet, and then Alice is going to come along and delete her tweet. That animation looks better, not over Google Meet. So what should be the outcome? Well, what is the outcome? What does Twitter actually do? Twitter does this, right? Bob tweet survives. Alice's tweet is deleted. And Bob's tweet has like this broken reference, right? Couldn't have happened in the world where Alice didn't tweet. So here's the time I want to ask people for input. Does anybody think that this, like what Twitter does in this particular example, what Twitter actually does, Facebook does the same thing. I'm sure every social network does the same thing. That this is either not meaningful or that you think that there's like a better answer in this particular scenario. If somebody thinks it's not meaningful or that there's a better answer, I would love to hear it because that would be interesting. Putting aside how we define this, like in this particular example.
I mean, it seems to me that, like you can't really delete tweets because someone could have taken a screenshot. So like you can't do anything better than this, right?
You're saying Bob could like have taken a screenshot of Alice's tweet and tweeted the screenshot out.
Yeah.
Right. That's true. So I think the point there is that like the environment's actions can depend arbitrarily on Alice's actions. But
right.
even so, I think like we could at least hope for this.
Right. I mean, well, maybe like the follow-on question then is like, should Alice have the right to delete Bob's tweet, which contained a screenshot of hers?
That's a very, so that's a very, I think, a very different question and a question we don't get into.
Sure.
We're not even going there. So to sort of in the particular Twitter example, our sort of guiding intuition is that sort of something like this, what's on the picture, is sort of a meaningful outcome, as opposed to both deletion as confidentiality and simulatable deletion, which have not meaningful outcomes. So the GGV definition, deletion as confidentiality, says that there's like nothing Twitter can do that would satisfy their notion of deletion. So it's sort of too strong. The simulatable deletion says that Twitter doesn't have to do anything. They could leave it like this, and it would satisfy simulatable. Somebody has a hand raised. I don't know how.
Yeah, I got a question. So I think intuitively, I think I agree with the right to delete. That's something that I wish I think I want to have. But in an attempt to challenge my moral intuition of trying to think of a thought experiment to see whether it can sustain the pressure test. Let's say I said something horrible in this meeting, right? And you all remember that. I would wish that I could delete that, but obviously it would be hard to delete it from everyone's mind. But let's say there is a way, technically. I can ask you guys to go through some brain surgery that removes nothing but my memory about my statement, right? Then do I have the right to demand that everyone do that and have you all carry that cost, right? So that's kind of analogous to the right to delete that we're talking about here. I guess I'm just curious of what are.
So I disagree that it's analogous to at least the example that's on the slide. So I think what would be analogous to what you're saying in the Twitter example is if Twitter also deleted Bob's tweet, like the tweet that's on the screen, still on the screen here, right? Because it's like Alice did an action. That action induced somebody else, Bob, to take some other action, right? And that action is, in this case, publicly visible. And so the example that you're giving is that once Alice says, oh, I wish I never did that, or I want to delete the action, I also want to delete all the downstream effects of my action. So in that case, Twitter would have to go and delete Bob's tweet. Or if Thomas took a screenshot of Alice's tweet and said, oh, my God, this is the most heinous thing, let me post it on Reddit, they'd have to go take down Thomas's tweet of the screenshot of Alice's tweet. So I'm not advocating for right now. I'm not even exploring the idea of this sort of undoing all of the effects, unrolling all of the effects.
But even before that, right? The analogous part is that by me asking that Twitter delete my tweet, I'm already asking Twitter to do something, right? And if there's a machine learning model behind it, I'm also asking that we remove something from that, some knowledge from that model. So I am demanding a bunch of actions already on Twitter, right? Is
Sure,
that
but you're demanding this action.
Mm-hmm. Right. Even then, right? I'm
the action that Bob's tweet is deleted.
Right, but I'm basically doing an action on the Twitter part, so such that my footprint is wiped.
Sure, but if somebody wants to do business, then those people should have obligations to the people they do business with. I think is like you're able to ask people to not send you emails. They have to do something in order to take you off their email list.
I see.
Okay, but I'm going to move on. So the question 2 is is there some way we can formalize deletion such that this is sort of seems like morally this is the outcome that is captured. So these are two, on their face, very different questions. Could be very different conceptions of deletion. Turns out we have one that we think manages to do both. And these were maybe not so clearly stated in our minds, but these were really sort of two motivating examples: adaptive, sort of a pan-privacy question having to do with pan-privacy, and a question having to do with Twitter. How can we make sense of these two examples? And they really informed a lot of what we do. So our contributions, just to summarize, is we have a new definition. We call it deletion as control. Along the way, we have to define adaptive variants of lots of things that have been studied in the past, like pan-privacy, history independence. So we introduce a handful of new definitions that are all adaptive. We show that deletion as control generalizes, which is to say weakens deletion as confidentiality. I'm ignoring technicalities. So in particular, confidentiality implies control. Again, ignoring technicalities of the models. We also show that history independence, a strong, an adaptive form of history independence, which is a notion that comes from cryptography and data structures. We show that history independence also implies deletion as control. And more than that, we sort of explain how machine learning, really the right way to view machine learning is as relaxations of history independence. The adaptive approximate version of history independence we define is a strengthening of all of machine learning, more or less. So we also show that differential privacy implies deletion as control. So in particular, we can show this concretely with two examples as sort of a batch, let's say, learning algorithm with central privacy, or let's say an online learning algorithm with pan-privacy and under continual release. Both of those will satisfy some version can be compiled into something that satisfies some deletion as control. And this isn't just learning, right? It's going to apply to more general things. And we have examples of functionalities that you can achieve that don't satisfy any of the previous notions. So something that's not by itself history independent and not by itself confidentiality, not by itself differential privacy, we can combine some of these things in limited ways to get something that is sort of new. It's a limited composition result, but it gets us an example of something different. So those are the contributions at a very high level. Today, I'm going to talk about just a few of them. So I'll tell you the definition. We'll talk about the machine learning adaptive history independence thing, and then differential privacy. Questions before I get into it? I scared away Pritish.
He said he had another meeting.
I see. All right. Cool. So let's dive into it. So here's I'm going to start with the definition of deletion as confidentiality, this definition from GGV, which we build on. We build on their sort of computational modeling and the definition of their whole approach. And so again, they think about a real world and an ideal world. So the real world is interaction between three arbitrary parties, a controller, this is Twitter, in an environment, which is a term borrowed from cryptography, which is every other party in the world, and Alice, who's some distinguished party that we care about. And in particular, these parties are going to interact, and Alice eventually is going to ask for her data to be deleted. That's the real execution. And the ideal execution is an interaction between the same parties, but where Alice and the controller never interact. So Alice sort of never input her data to the controller in the first place. So that's the real and the ideal world. There's a technicality that actually Alice shouldn't be able to send messages to the environment because Alice knows which world she's in, right? Alice can try to talk to the controller, and then her network keeps disconnecting, so she thinks she'll know that she's in the ideal world. She could tell the environment. So there's like this subtlety that I'm not going to talk about again. Those are the real and ideal worlds. And deletion as confidentiality requires that so that the controller C satisfies deletion as confidentiality if for all environments and players Alice, the view and the state in the real world looks like the view and the state in the ideal world. So the view is, I should have notated it here. I did. Yeah, it's the view of the environment. So everything the environment sees in the internal state of the controller. And why do we care about the internal state of the controller? Because then it sort of binding the state of the controller binds sort of all future evolutions of the system, for one. And for two, if the GDPR means anything, it means that Twitter has to delete my tweet, right? Somehow internally in the state of Twitter, I keep ragging on Twitter. I don't have any qualms with Twitter. Internally, there should be some sort of change in the data structure. So that's what GGV requires. So let's look at a particular example. So Alice tweets, and what does the environment do? The environment looks up Alice's tweet. What did Alice say? The controller says hi. Alice tweeted hi, and the environment tweets the phrase Alice said hi. Right. This is sort of Thomas's. You take a screenshot and you tweet it again. Exactly. Right. So that's what's happening on the left. On the right, Alice never tweeted. So the environment running the same code is going to ask for Alice's tweet and get nothing. And therefore say Alice tweeted nothing. Right? So these two worlds are completely distinguishable. So it doesn't satisfy deletion as confidentiality. Now we want to go to a different definition. Our definition is deletion as control. So imagine the same real execution, but I'm going to introduce a little more notation. In our case, Alice and the environment can interact arbitrarily. So this is a more general interaction. And I'm going to denote inside the controller, there's the state S, and there's the randomness R. So this is like the controller's random tape. If you think about, SGD, this is like the S in SGD, right? This is the random tape. Whatever the controller is doing, it's its randomness. And QE are the queries that the environment sends to the controller. The sub E is telling you it's the environment's queries. Q is telling you its queries. So this is like in the last slide, it's what did Alice tweet? Please tweet this, right? Those messages. We look at, instead of the ideal world on the last slide, this ideal world, which I'm going to call a hypothetical world because I like it better. In the hypothetical world, instead of the environment replaying its code in this sort of adaptive way, we have a dummy, which all it does is it resends the queries from the real world. Right? So the dummy just replays mindlessly replays the queries that the environment sent in the real world. Okay, and this controller has some randomness. R prime might be different, and it has a resulting state S prime, which again might be different than the state on the right. And so this R prime, and we'll get to an example with this replayed queries. We'll see it in a second. So this R prime is some there's some distribution over its randomness. It comes from some simulator, and this simulator gets everything as input. It sort of can see everything, which is to say the real randomness, the real state, and the queries that are issued, and it comes up with some other random tape R prime, and it can see everything because again we're not really thinking about confidentiality here, if that was bothering somebody. And what do we require? We say that C, the controller, satisfies deletion as control if there's a simulator, like in this blue box, such that for all environments and adversaries, with high probability, oh, there should have been an epsilon and delta here. So there should be an epsilon and a delta. You can't see my mouse. There should be an epsilon delta deletion as control. So I apologize. So C satisfies epsilon delta deletion as control. If with probability 1 minus delta, the state in the hypothetical world and the state in the real world are the same. You get to the same end state. And the randomness in the hypothetical world that got you to that state is distributed close to uniform, and like has close to the right distribution. So let's interpret this. I don't think we'll have that much time at the end for discussion. I realize this is going to go longer than I wanted. So ask questions if you have questions. So one way to think about this is that if the state S prime is the same as the state S, then we could have gotten to S prime somehow in the hypothetical world. Right? And in the hypothetical world, S prime, we got to S prime by way of the queries, QE, and by way of the randomness R prime. Those are the two things combined with the code of the controller that yield S prime. And so somehow the queries from the dummy, which is to say the real queries that the environment really sent in the real world, those queries, and this alternate randomness R prime, together they're an explanation for the real state of the world S prime. For the state S prime, which is equal to the state S. So the real queries and the alternate randomness together, they sort of explain the real state. That's sort of why we want the first thing. And why we want the second thing is that this explanation, at least the R prime part of this explanation, is plausible. Right? So it could be that QE in the hypothetical world is not plausible, but at least R prime is plausible. And I think I already said this, but requiring equality of the states is good because, for one, it requires equality of future states and future outputs. So the future evolution of the system is going to be the same if we just cut and paste the state from the hypothetical world to the real world. So that's the definition. And I'll show an example. I think there was a question, but let me show the example first. So here's some weird controller. All it does is it takes queries as bits as input, and it stores the XOR of all the bits, XORed with some random bit. Okay, so it's like XOR, it encrypts using a one-time pad R, XOR of all the bits it ever got as inputs, right? Like this is a weird controller. In the hypothetical world, the state is computed in the same way, right? It's the XOR of all the bits it ever saw. But instead of using the real randomness R, it uses some other simulated randomness R prime. And it's easy to see that if you pick R prime in this particular way, which is to say it's the state, whatever, this particular way, that if you do this XOR and you compute S prime, you get the state S prime is equal to S. So let's check that this satisfies our definition. So the states are equal with probability 1, and the distribution of R prime is uniform. Maybe that's the distribution on the right is a uniform distribution of over bits. So I think there's a question that we can take.
So I have two questions. So first off, you're saying the probability that S prime equals S is equal to 1 is greater than 1 minus delta. So I assume that means that there's a coupling between these two worlds under which this is true.
A coupling between these ones. Yeah.
Are you placing any constraints on that coupling other than like the existence of it?
The existence of it. Right now.
Okay.
I guess it might be interesting to think about what does it mean. So I guess the coupling and the simulator are sort of intimately related. So it might be interesting to think about, what does the runtime of the simulator really mean for the interpretation of all of this? I think that that's something that we don't yet have a really clear answer to. But I think you had a second question.
Yeah, so can you elaborate on what the dummy is required to do?
Like just in the definition, like what
Yeah.
it's doing. So we run the real world. So the distribution of these things is run the real world. That with a particular execution, that execution defines a set of queries QE, right? The dummy replays that set of queries QE. So every time it gets activated, there's like a whole execution model with interactive Turing machines here, and they get activated and deactivated, and they pass messages. Every time the dummy gets activated, it sends the next message in its sequence of messages until it's done, and then the execution ends.
So this implies some kind of constraint on what kind of interaction there is. Like, if the controller says, "Environment, can you please repeat back to me the following?" Then, the dummy can no longer answer that.
The dummy will not do it. Yeah, the dummy won't answer.
Okay.
But it's an arbitrary interaction on the left. It's the dummy that's being right. But so let's go here. So maybe I think so I think this is a segue into this example, right? So let's look at the example of this Twitter, this public bulletin board. So what's the real world execution? Let's just have the environment is running the same code as I had before. It asks for Alice's message and then it reposts Alice's message, right? That's what's happening on the left. On the right, the dummy asks for Alice's message, gets something back, and then reposts Alice's message from the real world, right? So this is like an implausible transcript in this hypothetical world, right? And you can construct things such that no computationally efficient dummy could possibly produce the real transcript in the ideal in the hypothetical world. You can come up with such a situation. But the point is that this is sort of true about this picture on the bottom right as well. And so the way we sort of interpret this, and now we're in interpretation land instead of math land, is that after Alice's data has been deleted, the lingering dependence in the state on Alice's message it sort of only exists if the environment's message depended on Alice's message. And in some sense, all of the blame for the dependence of the state on Alice sort of comes from these queries QE, right? Which are thereby sort of allowed to be implausible in the hypothetical world, because we're okay with that, because in the real world they actually happen, and we want to somehow connect the real messages in the real world to this world where Alice didn't actually participate. And this coming up with this sort of this ideal world and the way of coupling these executions was a lot of the conceptual work here, and we hit many dead ends before we sort of arrived at this thing that looks pretty simple. There was a question.
So in particular, this excludes the screenshot from being protected.
The screenshot, yeah, Bob could tweet the screenshot, and it would be no problem, right? But it would only be no problem if Twitter deleted the original tweet, right? So it's requiring. I claim that it's requiring the right outcome, right? Like the outcome that 5 minutes ago, 10 minutes ago, I asked for, is there a better outcome that you would prefer? Nobody really came up with a better outcome. This is the outcome that's being required here. Right? And so the theorem that I haven't told you is that this controller is if this controller is history independent, then it satisfies deletion as control. Okay, this controller that does this picture, like deletes Alice's tweet. Okay, so now what's history independence? History independence. Well, we know the story. The story is the same as the story we saw before. What does data deletion mean? But for data structures, well, you can delete a user can be deleted from the abstract data type that the data structure implements, but its effect might live on in the physical memory representation of that data structure. This is particularly a problem if you have like hash-based, like a hash table with open addressing, like this sort of thing can come up. And deleting data from a logical state of the data structure doesn't necessarily remove its influence on the memory representation, which can be disclosive. And so our actual goal is to limit the information of a data point from the downstream memory representation. Okay, this is like exactly the machine learning story. I just copy and pasted a few words. And so the ideal solution is sort of exactly the same. Like it should be the same if you reran the execution on this data structure, but with a different stream that was logically equivalent. So history independence in implementation is history independent if the memory representation is independent of the history of operations. It only depends on the logical final contents of those operations. In this paper, we have to generalize this to adaptive and approximate history independence, which hasn't been considered before. And so we have to do all that definitional work, but this is the intuition of what history independence is doing. And now let me suggest that machine learning, a new view of all of machine learning, at least like the definitional work of machine learning. So think about a data type. We're going to call the updatable ML data type, where this is like the abstract logical definition of this data type. It has some underlying state that's a data set X. And there's three operations: insert, delete, and output a predictor. Inserting inserts something into the data set X, deleting deletes something from the data set X. And outputting a predictor means run some ML algorithm on X and output the result, output the model that results. This is an abstract data type. You can sort of formally specify this as an abstract data type. And it's the case that basically all the definitional work of machine learning, they all propose various relaxations of approximate history independence, adaptive approximate history independence for this data type. So they're all relaxations of, in particular, most of the works don't actually consider the state itself. They consider the output sequence, like just the sequence of predictors that are output, which doesn't guarantee, any security against future arbitrary behavior. It doesn't guarantee that Google, in its heart of hearts, doesn't know your data. Only that whatever Google outputs doesn't know your data, right? So that's a mismatch. But there's other sort of ways that these definitions relax: adaptive versus not, general operation streams versus insert in a batch and then delete, symmetric versus asymmetric guarantees, approximate versus exact guarantees. But that like is sort of you can try to map out every definition as like relaxation of approximate adaptive history independence along various axes. So we don't show that machine learning satisfies deletion as control. We show that adaptive history independence satisfies deletion as control. And there's sort of this a little bit messy space of machine learning definitions, and their relationship is not exactly clear. I have just a couple minutes, and I only need just a couple minutes, so I'm going to soldier on and talk to you about differential privacy, and then we can wrap up, and hopefully we have a couple minutes at the end. So now differential privacy. Here's an example. Here's a particular mechanism that will a particular controller that I'll use as an example, built out of the Laplace mechanism. So this controller takes as input a sequence of data operations, insertions and deletions, and it maintains sort of an up-to-date data set based on this stream in the way that you think. It produces no output at this stage of the computation before September 1st. On September 1st, this controller runs the Laplace mechanism. So it adds up all these bits, xi, adds some Laplace noise, and it stores the result y, and erases the underlying data set d. And now it just has y, so a state is y. And then after it does this computation, it returns y. Like you query it, it'll return y. Whatever you say, it'll return y. Delete my data, here's y, right? It just returns y. That's all it does. In this controller, the randomness is the Laplace random variable. The state is either d or y. So that's the real world. That's the real controller. In this hypothetical world, if you remember, the dummy is replaying all the queries that come from the environment, but Alice is not involved. So what happens in this hypothetical world? Again, we build this data set d prime. We compute this y prime, which is the sum of the xi plus a Laplace random variable L prime. So this can be a different random variable. Then at the end of the day, this controller is always going to return y prime. So I claim that this satisfies deletion as control. I guess I could have written epsilon 0. So the states, so let's start with the distribution over the randomness. It's easy to see this particular L prime distribution, which is just L plus Alice's bit. These two things are you know, we know Laplace random variables, so we know these distributions are close. L prime and L are close in distribution. And exactly by construction, the states are equal with probability 1. So if you're at the end, then the y prime is equal to the y by construction. And if you're before this model is trained and the state is d or d prime, well, the execution ended when Alice deleted her data, right? So Alice is not in the logical state of d or d prime, of neither d nor d prime. So by history independence, the logical states of these data sets are the same, and therefore their memory representations are the same, right? And so the states are the same before September 1st or after September 1st. And so this is great. This is the Laplace mechanism, but we can just generalize this in sort of the obvious way. So instead of the Laplace mechanism, use an arbitrary DP mechanism, and the randomness R prime, we sample R prime conditioned on the states being equal. If that's possible, if not, sample it uniformly random. That's a footnote. But generally, sample R prime conditioned on the states being, the outputs being equal. And so I claim that, so this is sort of a lemma that's useful. I guess I didn't even state the theorem. This thing is going to satisfy deletion as control for any m that's epsilon delta dp. I think I stated on the next slide. And the lemma that's used to prove this claim is that if m and m prime are epsilon delta close on d and d prime, sorry, if m is epsilon delta close on d and d prime with the same distribution over randomness, then sampling R prime in this sort of conditional way induces a coupling, just like Thomas said, where the probability that the states are equal is at least 1 minus delta, and the distributions of R and R prime are epsilon delta close. That's sort of a lemma. You could generalize this, and sort of a general version of this simulator, right? This is giving us a simulator for R prime. And this is giving us a coupling that lets us prove things. A generalized version of all this is sort of underlies a lot of the proofs, including from history independence, including from deletion's confidentiality. Okay, so the main result here is that dp implies deletion as control with the same epsilon delta. And so theorem 1, we have two different theorems here. Theorem 1 is this particular controller that I just described a second ago. And theorem 2 is if you're in sort of a streaming setting and your mechanism satisfies event level adaptive pan privacy with continual release. Then this particular controller built out of that mechanism will satisfy deletion as control, right? The controller and the mechanism are not the same thing. And so here, this controller, what it does is it has this mechanism in its belly, and it's filtering the stream of queries that's coming to the mechanism. And it only sends a query to the mechanism if that user is not currently in its set D of users that have made queries. So a user makes a query. If it's in the set D, I just drop the query. And if it's not in the set D, I add that user to the data set, to this database dictionary D, and I pass the query along. To delete, all I do is update D, and I never update them. Never pass these queries along to them. This particular controller, if M is itself event level, adaptive, pen privacy with continual release, this particular controller satisfies deletion as control. Now, a lot of the inches of the paper, you can sort of see in this picture why sort of writing this paper is a bit of a slog, because we have to define adaptive pen privacy under continual release, adaptive history independence, adaptive executions of arbitrary Turing machines, and sort of we need all these things to be able to talk to each other, all these definitions to be able to talk to each other. So that's a lot of like the ink on the page is sort of devoted to this sort of stuff. And the invisible work is really, like I hinted at to Thomas before, it looks very simple, but basically everything in an orange box here took us a long, long time to get to, and many, many, many failed attempts. So this is the definition, and I want to just jump out. We're almost done. We started with these two questions. Does DP satisfy some meaningful conception of deletion? And does this sort of Twitter the natural thing that you would do with Twitter, does it also satisfy a meaningful conception of deletion? And maybe somewhat surprisingly, we get something that's meaningful that answers both questions, like the same conception. And so, just as a discussion, the one interesting point is, like, if you go way back to this, why did DP and machine unlearning sort of disagree? It was because machine unlearning required, after you've deleted everybody, required you ending up with a trivial model, right? And DP, if you have DP training, doesn't require that. And so it seems like maybe, at least in this particular example, DP or DP as an example, but our definition more generally is maybe capturing an individualized right to delete. Whereas machine unlearning, in the context of unlearning specifically, is requiring maybe something more collective, as a collective right. And these sort of, if you just forget computer science and go think about policy and human rights, like these are very different types of rights. And so maybe one of the differences between our definition and machine learning is maybe related to these differences. I don't really know. This is just amusing. Not amusing, it's one musing. It doesn't make me laugh. It's amusing. I'll stop there. There's lots of things, I think there was hinted at the beginning, there's lots of things that were like from a policy point of view, relevant to like a right to be forgotten, even a technical point of view, that we don't talk about. And here are some. And that's the summary. I'm sorry I went a minute over time. Thank you for listening and for all the questions. I'm happy to and keep discussing with whoever's available also.